Hello dear friends, so welcome back to my channel. I'm Gerard and I'm here to study maths together with you, and today we're going to learn about matrices. So it's plural, but you can say one matrix. So what is this? What is a matrix and what are matrices? A simple introduction is that, let's say you have two equations. So I'll write two equations here. Notice that they are linear equation. They are binomials, linear equation. We have two unknowns here, x and y, but these are lines. These are lines. They are not curves. And we want to solve them. We want to solve for x and y, do a lot of transformation and so on. So we use what we call matrices. So what is matrices? So we have our two equations. We can rewrite them in a matrix. So we'll write 5, 2, 1, 1, 3, 4. So we have just written these two equations in a matrix, and so that's another way to represent these informations. And we can do a lot of arithmetic calculations with this matrix. So this is an introduction to matrices. Sorry, I need to take the eraser. So what I'm going to write is the definition, a very simplest definition of what's matrix. So matrices, if you want def, I'll just write it like that. Def is just they are systems of linear equations. Once again, they are not curves, they are just lines. So linear equation. It's a system of linear equations. So we have put the two equations into a system. So a linear equation is in the form of a1 x plus a2 y is equal to b, where a1, a2, and b are real numbers. So they are real numbers. They can be negative, they can be fractions, they can be all these things. And of course, this is not equal to 0 and this is not equal to 0. In other words, so right now I'm understanding that in mathematics we have to define everything in a very accurate way, so which is quite difficult for me. But a1 and a2 are not equal to 0. So xy, what about xy, these variables? So they lies in the planes, in the plane xy, in the plane, sorry, and these are variables. Variables means that they can take many values. So basically that's what we're going to learn about. We're going to learn how to solve linear equations with the help of matrices. And general linear equation in the n variables, so we can have like very long linear equations in the form of plus plus a and x n. So this can take any value and can tend to plus infinity. Alright, so that was an introduction of what's of what's a matrix and what are matrices if you want. One matrix cannot help us really, but we have to make matrices. And so we're dealing with linear equations. And for example, if you have trigonometric is not linear, so logarithm or logarithmic, these are not linear functions if you want. Exponential as well, these are not. And there is also something called, well, for now I think that's enough. You have these curves. Quadratic equations are also not linear, and because they are simply not lines, they are to the power x and y. These variables are to the power a if you want, and a can tend to n, where n is real, and n are real numbers, and they tend to infinity or plus or minus infinity. Okay, so I will give you some example of non-linear. So remember that a1x plus a2y is equal to b is an example of a linear equation. It's very important because we need to know what we're doing with matrices. Why do we have to learn matrices and all those crazy arithmetic things if we don't understand why we need them? So that's my logic. So we have to learn how to use them. So for example, here we have this, and this is said to be not a linear, simply because here the power is 1, but here the power is half. So because it's to another power than 1, it's not going to be a linear equation, and which means that these are real numbers, yeah, but the variables cannot take powers other than 1. And here minus z plus xz. So here we have a product is equal to 4, for example. This is another non-linear or not linear. And of course, trigonometric functions, y is equal to sine x or cosine x, these are not going to be linear. It's going to be curves and so on. So we know that we need linear equations in our system of linear equations in matrices. The set of all solutions of the equation is called its solution set. The set of all solutions of the equation is called its solution set, or sometimes the general solution of the equation. So solution set, I will give you an example. We're talking about solution set. Solution set is when so let's say we have 4x minus 2y is equal to 1, okay, and x is equal to t, and this is just a parameter. And you will ask me, what's a parameter? It's just a value that that we have given to x. And so if we want to make y the subject of the subject of this equation, so we're going just to do like this. So we have 4x minus 2y is equal to 1. So we have minus 2y is equal to 1 minus 4x, and we have 2y is equal to 4x, just to get rid of the negative here. So, and then we have y is equal to 2x minus half by dividing by 2 on both sides. So we get this. So by replacing t, because we said, sorry, I'm trying to learn how to write in a very nice way. X is equal to t, so we can replace t here. So we will have t here minus half, so 2t minus half. Have replaced it, and we'll get a value. So it's going to be the solution set of this equation. So for x and y, we'll have like t and I don't know 2t minus half. This is a solution set. Okay, so solution set. And so it's important to understand what's a solution set when we're learning about matrices. So let's learn more about linear system, because that's what we are in right now. Linear system, lines, linear system, and a finite set of linear equations in the variables x, for example x1, x2, and is called a system of linear equations. A finite set of, so let's say you don't want to write x plus y plus z and so on is equal to 1. You don't want so many different variables. You can call it just 1x1, sorry, plus x2 plus x3 is equal to 1. So these are different variables, but you keep a certain homogeneity, let's say homogeneity. So by that I mean that you can call your variables like this. You can call your variable like this. And in matrices, that's how you do. You don't want to have x and y and x and y. You just have x, but they are coded with numbers. And this is called a system of linear equations, or a linear system. So we can have like 3x1 plus 3x2 is equal to 5. So let's say we have another equation, 4x1 plus 5 x2 is equal to 6. So I can write them in a matrix. So I will write like that. Oh sorry, I just made a mistake. So notice that the coefficients of x are under each other, and the coefficients of x2 are under each other. And so I will have 3, 5, and 5, 6. I should not put the arithmetic signs and the equal signs in the matrix. So this matrix can be called A, for example. A is this. Alright, so these values satisfy both equations. So if you want to solve this equation, so you can have values of x and y that are going to give both 0, for example. It means that if you put a value of x in this, it will give you y, and if you put the same, it will also give you the same result. Normally, roots, for example, oh, I don't know, let's say we have a line like this, you want those points or something, when y is equal to 0, when x is equal to 0, things like that. Okay, so not all systems of linear equations yes, not all systems of linear equations have solutions. For example, here, just for you to know, yes, we had this example here. I will write it in a smaller character so that we can work in a better way. Well, actually, it's not smaller, but more compact, but it's equal to -1. And the second one was 3x1 plus x2 plus 9x3 is equal to -4. Like I said, so we can have values. For example, if I'm trying to write in a nice way. So if x1 is equal to 1 here, and x2 is equal to 2 here, and x3 is equal to -1. So if you replace these values, you should get the result. For example, x1 will be 4 minus 2 plus -3. So this should give -1. Okay, because -5, this is -5, -1. So this is correct with these values, the solution set. Now let's do the second part. The second part is just like that. The same thing. We put the values what we put. So I will write it. Let me write in a very nice way. So again, the solution set. No, guys. Okay, x1 is equal to this, x2 is equal to this, and x3 is equal to this. So x1 is equal to 1, 2, -1. So we have, so that's going to be 3, that's going to be 2, and this is going to be -9. And the result is 3 plus 2, 5, 5 minus 9, -4, which is this result. So this is the solution set for these. I'll write it here. Solution set of this linear system or system of linear equations is a solution set here, right here, because it gives these values here. Okay, and that's what it means. And so now you know what is a system basis of linear equations. I am also learning, so I'm just also teaching myself by teaching. So, and a set of solutions, yeah, or solution set, sorry, solution set. So we know what these are now. We know they can sometimes be called general solutions. General solutions, either this or that. Okay, and just for you to know, sometimes we might have equations and we have, for example, these three equations, I think, go to 6, and we have x plus y is equal to 3. So I'm trying to put all the x's under the x's, so I didn't succeed. But here, for example, these are I can try to do like this, but this has no solution. No solution. The system of linear equation has no solution, simply because if you divide here by 2, the second equation, you divide by 2, I can use this sign, you will get minus x plus y is equal to 3. But just above equation 1 here, you have the same thing, x plus y minus x plus y is equal to 4. So 4 is not equal to 3. So we cannot solve this because they give different values. So then we say that this system of linear equations, has no solution. No solution. So just for you to know that if you have two equations, so we have two equations and they are equal to different numbers, so 3 is not equal to 4, so these two equations 1 and 2, so they cannot be solved. They cannot be solved. Alright, so that's about linear system, about solution set or general solution. We know all these things now. We know what is a matrix. It's just a way to represent linear equations. So let's continue. Intro to system of linear equations. A system of linear equation that has no solution is said to be inconsistent. So we have just seen this. So if we have, so this is I'm taking some habits here, equation 2, this is equation 2. If these are the two linear equations and there is no solution, so we just say that the system this is the system, because let's say we already transfer them in a matrix, so blah 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 blah, and this has no solution. It is said to be inconsistent. So now we are using terms like inconsistent, or terminologies, if you want, inconsistent. And on the other hand, if there is one solution at least, it is said to be consistent. So sys of linear equations, it can be either consistent or it can be inconsistent. Consistent means that solutions exist. Sorry, but I didn't manage. No solution. No solution. So now we know this. And for example, I will give you some graphs here. they have a plane of x, y. You have a line here, Since we're dealing with linear equations, they are all lines. So we have two lines. These two lines, line 1 and line 2, they are never going to be crossing each other. So intersections, no intersection, they are parallel, and there is no solution. There is no solution. Now, so I'm going to give you another example when there is one solution. We're still in the plane of y against x, and we have the line, the famous equation. For example, let it be L2, for example. Let's say it's just L2, and L1 is somewhere here, L1. So here there is a point of intersection, so there will be one solution because they intersect at this point. So there will be one solution. Now let's say there is another case, still in this plane. We have a line, yes, and we have another line that is just on it. I just put it in dotted line because if I will put it exactly on the line, you will not see it. But there are two lines at the same place. So here we have infinitely many solutions. So at all places on the line, there are solutions. They will intersect. Basically, there are two lines, exact lines. It can be, for example, y plus x is equal to 3, and then I just put 2y plus 2x is equal to 6. These two equations are exactly the same. I just have to divide by 2 here, and I will get the first one. So that's when you will plot the line, you will get the same line, and these two equations, or this system of equations, linear equations, they have has infinitely many solutions. So this is also possible. So every system of linear equation has either no solution, exactly one solution, or infinitely many solutions. So no solution, this is possible. One solution, they are not going to have two solutions, like like a curve and a line, or two curves. It's not possible, because a line it goes here and goes there. It's not going to go here and then back there. So it's going to cross only at one point. So it can have no solution, one solution, or infinitely many solutions. That's in the case I just showed when. So this is the first case, second case, third case, when they are just two same line. Yeah. Okay, that's about this particular how to say, this characteristic, or different cases that you might have. And so we have a certain way to represent data. Data is plural, datum is singular. So data, many datum, many data. So one datum, many data. Okay, some people say data also. Okay, So there is a way to represent the coefficients of linear equations in matrices. So I will write it. Let's say we have x1 plus x2 plus 2x3 is equal to 9. I'll try to write everything under each other. For x2 plus, no, it's going to be minus here, minus 3. I'm going according to my notes here. And then you have 3x1 plus 6x2 minus 5x3 is equal to 0. So as you can see, we have this variable, we have 3 variables, but we have also 3 equations. If we will put this in a system of equations, it's going to be, I will just do it like that, it's going to be a 3 by 3. This is also very important. The form of the equation is going to be, we are going to write the coefficients here. Here there is a 1, here there is a 1, here is a 2. It's going to be 1, 1, 2, 9. That's the number here. Remember, we don't put the arithmetic signs or the equal sign. Now we have 2, 4, minus 3, and 1. So 2, 4, minus 3, and 1. 3, 6, minus 5, and 0. That's why it's important to put all the x1 under each other, the x2 under each other, so that you can write this matrix perfectly like this. Here we have 3 rows, 1, 1, 2, 3, 3 rows. We have, actually it's 4 here. 3 rows and 4 columns. So 1, 2, 3, 4, 4 columns. Yeah, rows and columns. So this is how you represent data, and just to make it clearer, just to make it clearer for you. So we have all the data written in the matrix. We don't need the equations, but it can be written like this: a11 x. Sorry, I'll try to write in a more beautiful way. So it's going to be the coefficient, yes, just the coefficient, a11 x1 plus a12 x2 is equal to, let's say, b1. Then we have a21 x1 plus a22 x2 is equal to b2. So this means here the first means the row, and the second means the column, the second column, and so on. I think you got the idea. Let's try another one. 3, 1 x1 plus 3, 2 x2 is equal to b3. So by looking at this number here, we can already see that it's in the third row, but the first column. So this way of representing the coefficients is very important. And I'm going to erase here. So that was our first example. And so we have AIG. So the first subscribe These are subscribes, yeah. Sub sub Subscribes. These subscribes ij so indicates the equation in which the coefficient occurs. So the coefficient, this is, oops, it disappeared. This is for this one, the coefficient of x1, this x1 from this equation. So it has a unique number thanks to the fact that it's in the first row and first column. It has a unique number. So just like A12 has a unique number here, and it's in the first row, second column. So there is no other number that is going to be the same. So these are like their identities, or if you want to call them like this. So the first subscribe indicates the equation in which the coefficient occurs. This is number one, equation 1. So the 1 means equation 1, and the 2 means the second one indicates the unknown to which it multiplies. So 2 is x2. This is the variable. So the unknown or variable. Okay, so you can meditate on this. Thus, a is the coefficient of the first equation. Now here, thus a is the coefficient of the first equation, and multiplying to the second unknown, x2. Alright, I think you got this as well. So another way to talk about a matrix is that it's an array of numbers. What does that mean? It means that it's just that you have numbers, like list of numbers, you know. So, but that's how it looks to most people. When I look at this, these numbers and so on, and you remember the movie, you see like numbers falling in green, so what's happening? You have to read the matrix. But so these are arrays of numbers falling like this. So you are actually in the matrix. Alright, so enough of this. And so now we're going to learn some more terminologies. So we have matrix. Since we're talking about matrix, I'm using green. An array of numbers, yes. And there is something that we call, like, let's say you have I'll try to write a beautiful x1 plus x2 plus 2x3 is equal to 9, and 2x1 plus 4x2 plus, no, minus, sorry, 3 minus 3x is equal to 1. And then I have 3x1 plus 6x2 minus 5x3 is equal to 0. So I have these three equations, and I'm going to arrange them in what? In a system of equation. And this matrix, because matrices are going to be called different names depending on how they look and how the numbers are arranged and so on. So we're going to learn how to read the matrix So this is very interesting, reading the matrix just like in the movie. So this is very profound, this is very deep. So we're going to write this in this matrix, and when we're going to transfer these data to a matrix, we call this matrix the augmented matrix. The augmented matrix. So this is the augmented matrix. It's going to be 1 2 3 1 4 6 2 minus 3 minus 5 9 1 0. These are the data here, the coefficients. We're just taking the coefficients of each and also the numbers here on the other side of the equal to signs. So here is the augmented matrix. It's when you represent, just take the numbers from these equations, arrange in a beautiful and orderly way, and we put it in a matrix. This is called the augmented matrix. That's very important. So moving on, let me see the time. So we're going to make like about 1 hour video about matrix. If you can if you cannot like sit and watch for that long, you can pause and come back and so on. Actually, I'm looking at what's coming next, the Gaussian elimination, reducing the augmented matrix of a system that is simple enough that the solution of the system can be found by inspection. So reduce row echelon form. Okay, there is a guy, Gauss and something. So he invented this way of solving linear equations. So someone invented matrices. Someone, the architect in matrices, sorry, invented matrices, and what? So there are ways, once you have written the data here, there are ways you can find these. You remember there is x1, x2 and x3. So you can find these values, you can know their value, for example 1 2 3, and these are the values, the solution set. So there are ways to find them, and one of the way to find this information is called Gaussian elimination. So we're going to learn about this before ending this video because it's getting too long. So I will write it here, Gaussian. I'm not preparing my videos before making my videos, and no, prior to my videos. It's just like on the go freestyle and so on, completely, because I'm learning actually. Reducing the augmented matrix of a system that is simple enough that the solution of the system can be found by inspection. So by using the Gaussian elimination, so you had your augmented, remember you had your augmented matrix, right? You had your augmented matrix, and now you want to solve this to find the variables, yeah, that are actually the solution set, that is the solution set, sorry, and points of intersections of the lines, of course, point of intersections of the lines of equation, or because we had like a lot of equations here, and so we want to know where they all intersect. All the three of them intersect here. All right. So how do we find this point? We can solve like before. uh, you know, substituting here and there. Just like we saw x is equal to t, and then we put t in the equation to find y. So we have x is equal to t, and y is t something something. So, but when we have many equations, it's difficult to, because maybe one line is here, one line is, then we have a line intersecting here, or you have a line intersecting this here and there, but it's not going to satisfy. These are not the same solutions. So you see there are many solutions, many points, many solutions. So it does not satisfy all the lines. So matrix help us just to find the line where all are meeting exactly. Yes, here. That's wonderful. It's wonderful. So I will clean this. Actually, I'm learning. I didn't know these things myself before formulating them like that. That's the beauty of learning. So Gaussian elimination brings the augmented, I will write it, augmented matrix. It changed the augmented matrix by this method called Gaussian elimination. It put the matrix in what we call the reduced row echelon. This is a beautiful word, like sound French and so like erudite, reduced row echelon form. So it's going to look like this, guys. 1 0 0 1 0 1 0. This is not binary, but sounds like binary. But binary cannot have 2 and 3. So 0 1 and 1 0 0 1 0 1 0 2 0 0 1 3. So what you have to know is this. If you look here, you see that under the 1 there is a 0 here and 0 here. Under this one there is 0 here. So under the 1, these are all called, I think, pivot something. We will look at this term, but this is the first variable, x1, this is x2, and this is x3. Remember, because we put them in specific orders. So we know that x1 is 1, is equal to 1, x2 is equal to 2, and x3 is equal to 3. So x1 1, x2 2, x3 3. So just by looking at this reduced row echelon form matrix, we have a reading of the solution set, and we will learn how to reduce an augmented matrix into a row echelon form matrix by using the Gaussian elimination. There are many techniques, there are many techniques, many ways to reach the same solutions, but this is one of them. Gaussian elimination, so on. And I think reduced row echelon. Yes, there is a Gaussian elimination. I think, I might need to pause this and give an example of a Gaussian elimination example, so how it works. So let me try to do this. I will pause and I will give you an example of a Gaussian elimination. changing a matrix from an augmented matrix to a reduced row echelon form. Just in a moment. So I just want to tell you something. So this is a reduced row echelon form. This, what you're looking at here. And we see that the first at the top, at the left corner, top left corner, it's a 1, and this is called a leading 1. It's a leading 1 because what is the definition? If a row does not consist entirely of zeros, then the first non-zero number is a row in the row, is a 1. I will read it again because I'm a bad reader. If a row does not consist entirely of zeros, then the first non-zero number in the row is a 1. We call this a leading 1. So here we have a leading 1, here there is a 0, but then there is a first, a number 1, it's a leading 1. First number 1, and here 0, 0, 1. So we have the leading ones here. So that's how we call them, leading 1. If there are any rows that consist entirely of zeros, then they are grouped together at the bottom of the matrix. Let's say that there would be such a thing. So they are going to be at the bottom. We're not going to leave them, at the second place and so on, because we have 3 equations and we don't want to leave an equation that is equal to 0 somewhere in the middle. We can rearrange this. We can rearrange this. For example, the first equation could be at the second place, the third one at the first place, and so on. But this is arbitrary. We say that it's arbitrary. So in any 2 successive rows that do not consist entirely of zeros, the leading one in the lower row occurs further to the right than the leading one in the higher row. So which means that you have to have the, here at the top, the one has to be at the left, and at the bottom, the one has to be at the right corner. That's how, this is the principle. You cannot have the one here where I'm making dots here and then one here. It's not going to be in a reduced row echelon form. You have to follow certain principles, and each column that contains a leading one has zeros everywhere else. So 0 here, and the solution. 0 here, 1, and the solution. 0 here, 1, and the solution. These are rules. Let's say these are rules about the echelon, the reduced row echelon. And if you have a matrix only with zeros, there are no other numbers, just zeros, this is called a zero matrix. It's called a zero matrix. Yes. So we know how to read this. So x1 is equal to 1, x2 is equal to 2, x3 is equal to 3. So we know how to use this. So what I would like to do is just to, have some equations, and we worked our way from the augmented matrix, so just the data from the equations, and then by elimination reach to this. So I'd like to do this. There is an example here from the book that I am looking at. They say that there is x1. It's a little bit complicated, but okay. But at the same time, you're going to learn something new, just like I did for x4. equal to -1. So we have here we don't have anything. Here we don't have anything. And then we have x2. Here we don't have x1. These are equations, linear equation. And then we have 2x4 is equal to 6. And then we have nothing here, but we have x3 plus 3x4 is equal to 2. So this is a leading variable here, and this is a leading variable here, and this is a leading variable here. This variable is present in all of them, in all the three equations. We have three equations, and so this is a leading. We're going to call it the leading because it's like not present in the others. Yeah, the leading variable. There are so many terms. The leading variables are x1, x2, and x3. But we have we call it the free variable. There are so many terms. You know, once you're in matrices, you have to stay there and just use all these things every time, all the time, sorry, so that it's just like second nature. It's just a language. It's a universal language. Mathematics is a universal language. And so this is this free variable. So it means that we can, this is still in the, I think we can call it in a reduced variable as well. Reduce echelon, row echelon. I think it can be also said to be in a reduced row echelon. Not totally sure. Sorry. British English. And so let's see. How do I read this? So I can rewrite it in a matrix. In a matrix. So how will this look in a matrix? It's going to be 1, 0, 0, 4, -1, and 0, 1, 0, 2, 6. And it's not in a reduce. By definition, it's not in a reduce row echelon, because we said that in a row we have a 1 and everything else is 0 here. But here we have this free variable. But what we can say is x1 plus 4x is equal to -1. So x1 is going to be -1 minus 4x4. So this is something that we have, and we can express all, like for example, I will get rid of this. Alright, so we can express x1, x2, and x3 in terms of x4, because it's a free variable. And for example, we had t is a free variable, remember at the beginning. So what we have here, I'll write it. We have -1 minus 4x4. We have 6 minus 2x4, and we have 2 minus 3x4. So we have, this is 3, yes, x1, x2, x3. We have the three variables here, leading variables that we wanted in terms of the three variables. So this is not a totally reduced, how do you call this? Reduced row echelon. Let me get back to this. Reduced row echelon. This is not in a reduced row echelon. Sorry, this matrix is not in the reduced row echelon. It is just in a row echelon. This is just row echelon. Reduced row echelon is extreme. We cannot have any number here. It should be 0. Here also. It should be 0. So I will give you an example not of a reduced row echelon. So I gave you this. So what syntax is done. Okay, this is done. If we have an equation equal to 1, there is no solution for the equation. So another thing is, because now we are trying to learn all about matrices so that we can master this tool. If we have something like this, sorry, 0 here as well, the coefficient is 0. So we have 0, 0, 0 is equal to 1. So this is just, there is no solution for such an equation. 0 is equal to 1. What is this? It's nothing. Okay, there's no solution. And so we know what is a consistent system of equation. It's a system of equation that has a set of solutions. If it does not have a solution, it's inconsistent. Yeah. Next time I will talk about homogeneous linear systems. And for now I will stop. So just a review of what we did. We know what is a matrix. It's an array of numbers, matrices. So we know what is a system of linear equation. System of linear equation. Equations. So we know what are these, and we know what is a linear equation also compared to a curve and so on. And so we know what is a system. Yeah, means that they are arranged in a certain way. Yeah, with equal to something here, not 0, but okay. And we know what is an augmented matrix. Augmented matrix. We know when a system of equation is consistent. I will just write consistency here. So consistency means that we have solutions. We have solutions. If it's inconsistent, we don't have solution. So for example, if we have the same two equations, just time a factor, and they are parallel lines and so on. We saw that. And so now, what else? We know what is reduced row echelon form of a matrix. That's when we have 1, 0, 0, 0, a number, 0, 1, 0, 0, and a number, 0, 0, 1 0 and a number 0 0 0 1 and a number. So this is reduce row echelon form. And then we have also the row echelon form, where we can have a variable just like we saw. So that's about what we talk. We know that there is a leading one. These are leading ones here, leading ones here, leading ones here, ones here. And so what is a leading variable and what is um, a free variable? And we also know about Gaussian elimination. Gaussian was, I think, either an Australian or a German. Elimination, Gaussian elimination for row echelon form. Row echelon, in echelon and row echelon. Reduce row echelon. Reduced. So we have reduced row echelon form or just row echelon form. So in reduced you have only 1 0 0 and the number. Alright guys, so that's more than 1 hour of explanation about the matrices. That was an introduction. I hope you like it. I hope that it's helpful. And so I need to learn more. It's already 2:40 a.m. so I have to be quick. Alright, see you in a bit. I will make another video anyway. Thank you for watching. Like the video, share it with your friends if they're learning matrices, and subscribe to my channel so that you don't miss on my new videos. Bye.